All right, let's solve a little mystery from the world of C programming. Have you ever looked at one of your structs and wondered why it takes up more memory than it should? It's like there are these ghost bytes hiding in your code. Well, in this explainer, we're going ghost hunting. Okay, so let's start with Exhibit A. We've got a really simple C struct here. Inside, there's just a char, which we all know is 1 byte, and a short int, which is 2 bytes. So, do the quick math in your head. 1 plus 2, what do you think the total size should be? Take a guess.
If you landed on 3 bytes, you're not alone. I mean, that's what the math says, right? But here's the twist. When we ask the C compiler, it looks us straight in the eye and says the answer is 4 bytes. So, where on earth did that extra byte come from? That is the mystery we're here to solve today.
To get to the bottom of this, we have to start with the motive. Why would a compiler, which is supposed to be all about efficiency, intentionally add extra, unused space to our data? Well, as it turns out, it's all about keeping the CPU happy, and it all comes down to performance. And that brings us to the key concept here, data alignment. You see, data alignment is all about how we arrange our data in memory so the CPU can grab it in the fastest, most efficient way possible. And trust me, happy CPU is a fast CPU. To see what I mean, just look at this. Think of memory as being set up in these 4-byte wide banks. If a 4-byte integer lines up perfectly with one of these banks, meaning its address is a multiple of 4, the CPU can snatch it all in one go. One cycle, done. But if it's misaligned, say it starts at address 1, now the CPU has to do 2 separate reads to piece the whole thing together. That's literally double the work, and that is a huge performance hit. So because of this, every data type has its own natural alignment requirement. A char can sit anywhere, so its alignment is 1. A short needs to start on an address that's a multiple of 2. An int needs a multiple of 4, and a double needs a multiple of 8. These are the fundamental rules of the game that the compiler has to follow. Okay, so if alignment is the motive, then what's the method? How does the compiler actually enforce these rules? Well, this is where our invisible culprit finally shows its face. We're talking about structure padding. So what is structure padding? Well, it's pretty simple, really. It's just the compiler automatically and silently inserting empty bytes into our structs. It uses this padding to kind of nudge the other members around until every single one of them is sitting perfectly on its required alignment boundary. So, let's go back and solve our original case. Remember struct A BT? First, the compiler places the char at address 0. It takes up 1 byte. But wait, the next member, the short, needs to start on an even address, a multiple of 2. To make that happen, the compiler slips in 1 byte of padding. Now, the short can start at address 2. So we've got 1 byte for the char, 1 byte of padding, and 2 bytes for the short. And boom, total 4 bytes. Case closed. Let's try another one just to make sure we've got it. Here's struct BT. It starts with a short, which takes up the first 2 bytes. No problem. Then comes a char, which takes 1 more byte. We're now at a total of 3 bytes. But hold on, the next member is an int, and it absolutely must start on a multiple of 4. So the compiler adds 1 padding byte to push the int over to address 4. Add it all up. 2 plus 1 plus 1 for padding plus 4 gives us a grand total of 8 bytes. All right, feeling good? Let's tackle a trickier one, struct CT. First, we have a char, that's 1 byte. Next up is a double, which needs 8-byte alignment. So to get from address 1 up to a multiple of 8, the compiler has to add 7 bytes of padding. Then we place the 8-byte double, and finally the 4-byte int. So that's 1 plus 7 for padding plus 8 plus 4 comes out to 20 bytes. Seems logical, doesn't it? Nope. The compiler comes back and tells us the actual size is 24 bytes. What is happening here? We found those 7 padding bytes between the members, but where did these other 4 mystery bytes come from? It turns out there's one more rule we haven't talked about yet. And here it is, the real kicker. It's not just the individual members that need to be aligned. The structure as a whole also has an alignment requirement, and that requirement is set by the largest member inside it. Why? Well, think about an array of these structs. This rule ensures that for every single element in that array, all of its members will also be perfectly aligned. So here's the final piece of the puzzle for struct CT. Its biggest member is that double, which has an 8-byte alignment. That means the struct's total size must be a multiple of 8. Now, we calculated that the members plus the internal padding added up to 20 bytes. What's the next multiple of 8 after 20? It's 24. So the compiler tacks on 4 extra bytes of tail end padding, just to round the total size up.
Okay, so we've cracked the case. We understand the rules of the game. Now for the fun part. We can become detectives in our own code. Let's talk about how we can use this knowledge to our advantage and write structs that are way more memory efficient.
Here's a look at all our suspects lined up. You can see what we've thought the size should be versus what it actually is. And just look at the difference between struct CT and struct DT. They have the exact same members, but one takes up a whopping 24 bytes and the other only 16. What gives? The answer is probably the simplest, most effective trick in the book for minimizing padding. Reorder your members. Seriously, if you declare them from largest to smallest, you naturally create a layout that requires the least amount of padding to satisfy all those alignment rules. And this chart really says it all. In struct D under T, all we did was move the double to the front, followed by the int, and then the char. That one simple change saved us 8 bytes. That's a 33% reduction in memory. For free! All you had to do is change the order of a few lines of code. But what if you need to go a step further? What if you need to eliminate every last byte of padding? Sometimes, when you're dealing with network protocols or specific file formats, you need absolute byte-for-byte control. Well, for those situations, you can pull out the big guns. Most compilers give you a way to force the issue, to just override the default behavior. In GCC, Clang, and many others, it looks something like this: hash pragma pack 1. You can think of this as a direct order you're giving the compiler. What you're doing here is basically telling the compiler, hey, forget everything I just taught you about alignment. I want you to pack every single member right up against the next one, with 0 padding. This gives you the smallest possible size, but you have to remember that trade-off. You might pay for that memory savings with slower CPU access times because of those misaligned reads we talked about. Just look at the difference it makes on our most wasteful struct. Struct CT, which was a bloated 24 bytes, shrinks all the way down to a lean 13 bytes when we pack it. That's just the raw size of its members. 8 for the double, 4 for the int, and 1 for the char. Nothing more. So, what should you do in your own code? Well, here's your toolkit. First, always try to optimize by reordering members. It's the best of both worlds. You get great memory usage and great performance. Second, only use packing when you have a very specific reason, like matching a network protocol exactly. And third, remember you can always do nothing. Sometimes the clarity of your code is way more important than saving a few bytes here and there. So, there you have it. We've uncovered the motive, the method, and the solution to the case of the padded struct. Those invisible bytes aren't so invisible anymore, are they? The only question left is, now that you know what to look for, where are you going to find these hidden costs in your own code? Thanks for joining this explainer.